In this lecture, we'll discuss the definitions of acids and bases, how to define acid and base strength. We'll also learn how to predict acid-base reactions from pKa values, and we'll look at the structures of organic acids and bases and how to relate structure to pKa value. We'll primarily use three definitions of acids and bases in this course. The Arrhenius definition, which defines an acid or base on whether it produces hydronium or hydroxide. The Bronsted-Lowry definition, which defines an acid and base in terms of whether it's accepting a proton or donating a proton. And the Lewis definition of an acid and base, which defines it in terms of whether it is accepting electrons or donating electrons. It should be noted that all three of these definitions are coherent. In other words, they don't contradict one another. In many cases, one or all definitions can be used to describe certain phenomena. The Arrhenius definition depends on a substance's behavior in water. Anything when added to water that produces hydronium ions is called an Arrhenius acid. And any compound that when added to water produces hydroxide ions is called an Arrhenius base. And so water is the key here, the behavior in water. Without water, we can't define an Arrhenius acid or base. Let's look at an example of an Arrhenius acid. Hydrofluoric acid, HF, is an Arrhenius acid. When you add it to water, it produces a hydronium ion and a fluoride ion, seen on the right-hand side of the screen. We can actually draw arrows to show how this transfer is taking place. In this red arrow, we see that a pair of electrons on water is being used to form a new bond to a hydrogen atom in hydrofluoric acid. Since hydrogen can only have two bonds, its bond to fluorine has to break. And one key concept to keep in mind, whenever bonds break, they always break towards the more electronegative atom. And so the HF bond breaks, and the two electrons in that bond move towards fluorine. So oxygen has gained a bond, and fluorine has gained a pair of electrons. That gives us the hydronium ion and the fluoride ion. Now, notice that this is an equilibrium reaction, right? The two arrows in the middle tell us that this reaction proceeds left to right and right to left. But equilibrium doesn't mean equal. It only means that the rates forward and backward are equal. It doesn't mean equal amounts. And so the strength of an Arrhenius acid, or any acid for that matter, depends on how much hydronium ion exists at equilibrium. If the equilibrium lies farther to the right and there's more hydronium ion, we'll have a larger equilibrium constant and therefore a stronger acid. Remember that an equilibrium constant is defined as the concentration of products divided by the concentration of reactants. We can see here in this acid-base reaction at the top, HCN reacts with water to produce a hydronium ion and cyanide. And the equilibrium expression is the concentration of hydronium ions. And concentration, remember, is indicated by brackets, right? These square brackets mean concentration. And concentration can take many different units. It could be moles per liter, molarity. It could be parts per million, right? That depends on the problem. But the products of the concentrations of the products divided by the concentration of the reactants gives us a value called Ka. This is the equilibrium constant for acids. The A means acid. Notice the difference between the top equation and the bottom. If we take water out of the equation, then we simply have a dissociation reaction, right? HCN is dissociating, or the bond is breaking, right, between the hydrogen and the carbon to produce a proton and cyanide. This is very similar, and the Ka is defined in a similar way. One thing to remember is that the larger the Ka value, the more hydronium ion is being produced, and the stronger the acid is. Here we see an example of an Arrhenius base, sulfide. Sulfide, when it reacts with water, produces hydroxide and hydrogen sulfide as the conjugate base. We can draw a mechanism for this reaction using curved arrow notation. Here you see a lone pair on sulfide is being used to form a new bond to the hydrogen atom in water. Again, hydrogen can't have more than 2 bonds, and so the HO bond has to break, and it breaks towards the more electronegative atom, oxygen. This produces hydroxide and hydrogen sulfide. Not surprisingly, hydroxide is also an Arrhenius base. When hydroxide reacts with water, it produces hydroxide. Or another way to think about it is hydroxide simply dissolves in water, which makes it an Arrhenius base. If we wanted to think about hydroxide undergoing a chemical reaction with water, we could again draw the same curved arrow notation, the same mechanism, to show how the electrons are flowing in this reaction. A lone pair on the oxygen of hydroxide could be used to form a new bond to the hydrogen in water, and then breaking the hydrogen-oxygen bond towards oxygen. That gives us hydroxide and a new water molecule. It's of course impossible to distinguish between the hydroxide and water molecules on the right and those that are on the left. Just like with Arrhenius acids, we can write an equilibrium constant for an Arrhenius base. This is called the Kb. It's again the product of the concentration of the products divided by the product of the concentration of the reactants. Again, concentration is indicated by square brackets. The larger the Kb means the more hydroxide there is in solution, and thus the stronger the base. We'll use the same example, hydrofluoric acid, to show that it's a Bronsted acid. Again, you can see that water is using a lone pair to form a new bond to hydrogen and breaking the HF bond to produce hydronium and fluoride. But now to define the acid, we'll define it in terms of what's happening to the hydrogen atom. So HF is donating a hydrogen atom to water, right? It's donating this hydrogen atom here to the oxygen in water. And anything that is a proton donor, and proton is another word for hydrogen atom. Anything that is a proton donor is called an acid. Anything that is a proton acceptor is called a base. And so we could actually label water here as a base. It's accepting the hydrogen or proton, and the acid is donating it. So the Bronsted definition gives us the same categorization of acid and base, but we're looking at it a little bit differently. Because we no longer need water to define a Bronsted acid or base, we can also simply write a dissociation reaction for a Bronsted acid to produce a proton and its conjugate base. I could also draw a mechanism for this reaction, just like I did before, if I draw the structure and then use curved arrow notation to show that the bond between the hydrogen and the fluorine is breaking. Again, bonds always break toward the more electronegative atom. That also shows that HF is a Bronsted acid because it can dissociate into a proton and a conjugate base. If we define a Bronsted base in the same way, we would say that it is a proton acceptor. A Bronsted acid is a donor, a Bronsted base is an acceptor. And so in this case, water is the Bronsted base. It is accepting the hydrogen atom, again from HF, to give hydronium ion. Notice that the curved arrow notation doesn't indicate who is accepting or donating the proton necessarily. The curved arrow notation, the red and the blue arrow here, are only showing you the movement of electrons when forming a bond, that's the red arrow, and when bonds break, that's the blue arrow in this case. So you have to look at the products to determine who accepted the hydrogen or the proton and who donated the hydrogen or the proton. Another concept to consider when talking about acid-base reactions is the idea of conjugates, right? And conjugates means that there's an acid and base on both sides of an equation. So on the left side of this reaction, we know that water is the conjugate base. It's accepting a hydrogen, and hydrofluoric acid, HF, is the acid. It's donating the proton. But if we look on the right-hand side of the equation, we can also categorize those products as an acid or base, because we know that all acid-base equilibria are just that, equilibria, right? This reaction can go in the opposite direction. And so if I'm moving from right to left, then the hydronium ion becomes the Bronsted acid. It's donating one of its protons to fluoride. And vice versa, fluoride is a base then, as the reaction moves from right to left. Fluoride is accepting a proton to become HF. And so we call these conjugate pairs. In other words, water on the left is a base, and its conjugate acid is hydronium ion on the right. They are related, right? And a good rule of thumb is that a conjugate acid always has one more hydrogen than a conjugate base. If we look at hydrofluoric acid, right, on the left, HF is the acid. Its conjugate base is fluoride on the right. The only difference between those two compounds is one hydrogen atom, or one proton. Again, a conjugate acid always has one more hydrogen than a conjugate base, and so the opposite would be true. A conjugate base has one less hydrogen than a conjugate acid. So in every acid-base reaction, right, we can find conjugate pairs. Here's an interesting case that shows the autoionization of water. Right, so we have seen water act as both an acid and a base in these examples. And that's true whether we're using the Arrhenius definition or the Bronsted definition. So we could imagine a water molecule reacting with another water molecule. And one of the water molecules is accepting a hydrogen, right? That's this first one here, which makes it a Bronsted base. The other water molecule is donating a hydrogen. That makes it an acid in the Bronsted definition. And that gives us hydronium ion and hydroxide ion, right? This is called the autoionization of water, right? And this happens all the time. The equilibrium lies far to the left. It doesn't happen to a great extent, but it does happen. And this is how we define pH of neutral water, by the amount of hydronium ion and hydroxide ion due to the autoionization of water. Here are two more examples that illustrate the point that water can act as both a Bronsted base and a Bronsted acid. In the top example, water is acting as a Bronsted base. It is accepting a hydrogen atom, a proton, from an acid. Again, we can use this curved arrow notation, right, which is showing how the electrons are involved in that transfer. And in this example, if water accepts a proton, then we get hydronium ion as a conjugate acid. In the bottom example, we see that water is acting as a Bronsted acid now, right? We have a base, right? We'll talk about this a little bit later. This is called amide, a nitrogen with two lone pairs and a negative charge. And we see that this base is accepting a hydrogen from water. And by accepting, we mean it's using a lone pair to remove one of the hydrogens from water to form a bond to it. And that breaks the hydrogen-oxygen bond towards oxygen. Right? So in this example, hydroxide ion then is the conjugate base of the acid water. Okay, so again, water can act as both an acid or a base, depending on whether it's donating a proton or accepting a proton. In the top example, it's a base because it's accepting, And in the bottom example, it's an acid because it's donating. So a logical question is, why do we need multiple definitions of acids and bases? This example illustrates the power of the Bronsted definition. Here we have an acid-base reaction, and notice that there's no water, right? We're not producing any hydronium or hydroxide as products, and so the Arrhenius definition wouldn't work here. But we can still define the reactants as a base and an acid using the Bronsted definition. On the left here, you can see ammonia is accepting a proton from hydrochloric acid. Right? This is a Bronsted acceptor. And so that means it's a base. Right? Again, the arrow is how the electrons are doing the accepting. The lone pair on nitrogen is being used to form a new bond to the hydrogen of hydrochloric acid. But to determine who the acceptor is, we don't necessarily look at the curved arrow notation, we look at the products. Right? We can clearly see that ammonia accepts a proton and it becomes an ammonium ion. Right? Let's make sure we understand the difference in those words. This is ammonia, right, the compound, and this is an ammonium ion. Right? And those are linked together. They're conjugate pairs. Right? The conjugate acid of ammonia is ammonium, and it's gained one hydrogen atom. All right. Likewise, hydrochloric acid is an acid here because it's donating a proton, right? And it's donating a proton to ammonia, right? So hydrochloric acid is donating, and that's why it's an acid. All right. So the point here is we don't need water then, right, to define whether these reactants are acids or bases. Now, if we look at the products, we can also call those acids and bases by considering the reverse reaction from right to left in this equilibrium. And we see that the ammonium ion is donating a proton to chloride, right? And if it's donating a proton, that makes it an acid. And likewise, chloride is accepting a proton as this reaction moves right to left, and that makes it a base. The conjugate pairs then, right, are the compounds that are similar, right? One has one more proton, one has one less. Let's move on now and talk about how we measure the strength of an acid or even a base. We already said that we can define this constant called an acid dissociation constant. That is the Ka. And that Ka is just an equilibrium constant for an acid, right? And that is the product of products divided by the product of reactants. Typically in organic chemistry, we're working with either very strong acids like hydrochloric acid or sulfuric acid, or pretty weak acids. And so the Ka values are usually quite small. Right? A typical Ka value is something like 1 times 10 to the negative 8th. Right? That's a pretty small value. And so organic chemists tend to report the strength of an acid using a unit called pKa. And the P in pKa represents the negative log base 10 of Ka. Right? So if I had a Ka of 1 times 10 to the negative 8th, the log base 10 of that would be negative 8. Right? So log base 10 of 1 times 10 to the negative 8th is negative 8. And then the negative of log base 10 of that is a positive 8. Right? So I can convert Kas into pKas by taking the negative log. Right? And vice versa. I can go in the opposite direction. Now what that means is the smaller the Ka, the larger the pKa. That's important enough to write down. Right? The smaller the Ka, the larger the pKa, And a larger pKa means a weaker acid, right? Because this is an inverse scale. The opposite is true as well. The larger the Ka, the smaller the pKa, and the stronger the acid. So this slide gives you an idea of the range of pKa values that you might have for inorganic acids as well as some organic acids. So on the left here, we see that acidity is increasing as we move up this list, right? So strong acid here at the top and weak acid here at the bottom, right? And if you look at the pKa values, right, you can see that strong acids have very small pKa values and weak acids have very large pKa values, or at least larger. Okay, but what's important here is that the scale is relatively compressed. Because this is a log-based scale, right, we're looking at numbers really no larger than 62, right, and then all the way down to -4 for hydrochloric acid. So that's a manageable scale. We can always convert pKa's back into Ka's, and you should do this as practice. I'll do just one for you as an example. Right? If the pKa of water is 15.7, then that means its Ka is 1 times 10 to the -15.7. Right? That's pretty small. Water is a fairly weak acid. It's got a small Ka. And this diagram on the right-hand side here gives you some more examples to help you appreciate the mathematics behind the negative log base 10. So practice that, take a look, and see if that makes sense. Next, we want to talk about the structural effects on the strengths of acids. This is the real power in this course. We don't want to necessarily memorize hundreds or even thousands of pKa values for organic compounds. We want to be able to predict what their pKa is just by looking at their structure. So there are several different factors of an organic compound structure that can affect its pKa. And the first is the electronegativity of the atom losing the proton. All right, let's write that down because that's important. Of the atom losing the proton. Remember, proton just means hydrogen atom. Right, so on the bottom here, we see a very general equation. Ha represents an acid, and it's dissociating, right? In other words, the bond is just breaking towards the more electronegative atom into a proton and some conjugate base, A-, right? So this is very general, right? I'm not telling you what A is, okay? And the general rule of thumb for this electronegativity principle is the more electronegative A is, the lower in energy it is. And the lower in energy it is, the more, that essentially means more stable, the further this equilibrium lies to the right. Equilibria always lie further or closer to the more stable side. And so if A- becomes more stable because it's more electronegative, the equilibrium lies further to the right, and that makes the Ka bigger. Right? So let's say that again. Right? The more electronegative the conjugate base is, or at least the atom losing the proton, the more stable it is. And the more stable it is, that means the equilibrium lies further towards that side, and that means the acid is stronger than some other reference case. So to illustrate this point, let's look at 4 examples. In the top row, from left to right, we have methane, ammonia, water, and hydrofluoric acid. Right? As you might predict, hydrofluoric acid is the strongest acid. Methane, on the far left, is the weakest. But let's see if we can reason through this using this electronegativity principle, right? So if we look at the atoms that are losing the hydrogen, those are the atoms that are in bold, right? So the carbon atom, the nitrogen atom, the oxygen, and the fluorine, right? And I've written the conjugate bases down below. How did we get the conjugate base? Well, conjugate base always has one less hydrogen atom than the conjugate acid. And if we just imagine a dissociation in which no other thing is accepting that hydrogen, then I can draw a mechanism where the atom to hydrogen bond breaks and the atom gains a lone pair and becomes negatively charged, right? So I can do that in all of these cases. I can draw a mechanism to show how I get from the conjugate acid to the conjugate base, right? And they're pretty simple here. All right, so first, let's think about what is the electronegativity of carbon, nitrogen, oxygen, and fluorine relative to each other. Well, we know that electronegativity increases left to right in the periodic table. And if you look at where these atoms are in the periodic table, you'll see they're all in the same row. And so electronegativity is increasing left to right here, the way that I've written these examples. Fluorine is the most electronegative. Carbon is the least in this series. Our electronegativity principle says the more electronegative the atom that's losing the hydrogen, the more stable that conjugate base is, and the more stable the conjugate base, the stronger the acid. So if we look at the conjugate bases below, we could say that fluoride is the most stable conjugate base. And that's just a fancy word for it's the lowest in energy. I'm going to use the letters N, R, G to mean energy. And on the opposite end, that means a carbon with a negative charge is the least stable, which is a fancy word for it's the highest in energy. So how does this relate to acid strength then? The lower the energy the conjugate base, the stronger the acid, right? And so hydrofluoric acid is the strongest acid with a pKa of 3, and methane is the weakest acid with a pKa of 60. Remember, pKa is an inverse scale. The bigger the number, the weaker the acid. The smaller the number, the stronger the acid. I forgot to mention one very important thing, so let me go backwards, back to slide 19. This electronegativity principle only applies when the atoms losing the hydrogen that we're comparing are in the same period or same row of the periodic table, right? That very first point right here, right? So let me say that again. The electronegativity principle only applies when the atoms losing the proton are in the same row of the periodic table. Let's use the electronegativity principle when the atom losing the hydrogen is the same, right? So if we look at case A here, right, we see that the atom losing the hydrogen is the oxygen in each case, right? It's not iodine, bromine, chlorine, it's oxygen. If we were to write a dissociation mechanism, it would look like this. And so clearly, the electronegativity of all three of those oxygen atoms is the same, if we were to look that up in a table. But the point here is the electronegativity of distant atoms can also have an impact on the stability of the conjugate base, right? And between iodine, bromine, and chlorine, chlorine is the most electronegative, right? It pulls electrons towards itself the most. And what that means is, if we draw the conjugate base, and I'll do that for just the far right-hand example. In all cases, we're going to end up with an oxygen with a negative charge. But because chlorine is electronegative, it can actually pull that negative charge towards itself, right? And try to distribute or spread out the electron density that's on oxygen. And that's a good thing, right? When distant atoms can pull electron density away from negative atoms, that makes them lower in energy. So I would say that this is the most stable conjugate base in that series in A, and most stable just means lowest in energy. We call this the inductive effect. The ability of distant atoms to pull electron density towards themselves and reduce the amount of electron density on negative atoms. This is called the inductive effect. And it's doing that pulling through the sigma bonds, right, that are attaching all of those atoms. Iodine is the least electronegative of these atoms, and so it does the least pulling. And if it does the least pulling, right, then the conjugate base is the least stable. It's the highest in energy, right? And so in summary, that means that HOI is the weakest acid, and HOCl is the strongest acid. So this is an extension of that electronegativity principle. Even though the atoms losing the hydrogen are all the same, distant atoms can still have an effect, this inductive effect. Now, the previous example might be one that you see in a general chemistry textbook. Let's get to some organic chemistry. Let's look at two organic acids. So the top one here is ethanol, and most of you are familiar with ethanol. It's usually the alcohol that's in antiseptic. It's also the compound that's in alcoholic beverages like beer and wine. Below it is trifluoroethanol. So let me point out that there are 3 fluorines attached to the carbon on the far left. So they are very similar structures, right? The only difference is I've exchanged hydrogens for fluorines. But if you look at the pKa's of these compounds, and those are written in green on the far right, you see that they're very different. The pKa of ethanol is 16, and the pKa of trifluoroethanol is about 11. And each pKa unit difference is a factor of 10. So 16 minus 11 is 5. We could say that trifluoroethanol is 10 to the 5th. 10 to the 5th times more acidic than ethanol. That's huge, right? That's very big. All right, how do we explain that? Well, if we look at the atoms that are losing the hydrogen, we can see that in both cases, it's this oxygen right here. Right? This looks like a dissociation reaction, right, where this bond is breaking. And that gives us conjugate bases where the oxygens are both negatively charged plus our proton. And the conjugate base for trifluoroethanol has the lowest energy. It's the most stable. And the reason is because the 3 fluorine atoms are highly electronegative, and they're pulling the electron density away from the negatively charged oxygen through those sigma bonds. That makes the conjugate base more stable. Remember, the more stable the conjugate base, the further the equilibrium lies in that direction. And if the equilibrium lies further to the right, Ka will be bigger, and therefore pKa will be smaller. That's the definition of a stronger acid. All right, take a minute to think about this question, right, or this problem. Go ahead and pause the video and see if you can rank these 4 acids in order of acid strength. So from least acidic to most acidic. And I'll give you a couple hints before you consider the answer. In all of these cases, the atom that's losing the hydrogen is the oxygen right here, right? And so the atom is the same in all 4 cases. See if you can use the inductive effect to determine which conjugate base is the most stable and therefore which acid is the strongest. And I'll give you a little clue here. Distance matters. The closer electronegative atoms are to the conjugate base with the negative charge, to that atom, the stronger the inductive effect is. All right, did you pause the video? Did you give this a try? What did you come up with? So one of the clues here are the fluorine atoms. Some of these acids have them, some don't. Some have different numbers of them, and they appear to be at different distances from the atom losing the proton. All right, so those are all going to be important factors. The first thing that we should consider, though, is what does the conjugate base look like for A, B, C, and D? Well, it looks like this. It's called a carboxylate anion. And by the way, all of these acids at the bottom are called carboxylic acids. We'll talk more about functional groups in a later lecture, but a carboxylic acid is any compound that has a carbon-oxygen double bond attached to an OH group. And that's what we see in all these cases. So the carboxylate anion is the conjugate base, and that results when I dissociate the oxygen-hydrogen bond, again breaking the bond towards the more electronegative atom. The other product, right, for all of these acid-base equilibria is the proton. All right, so the question we have to ask is, which carboxylate anion is the most stable for these carboxylic acids? And the most stable carboxylate anion will come from C, because C has 3 fluorine atoms, and they are the closest to the oxygen losing the hydrogen atom. They will better be able to do the inductive effect and pull the negative charge from oxygen towards themselves. The more stable the conjugate base, the stronger the acid. And so C here is going to be the strongest. Right? If by that same reasoning then D is going to be the weakest acid, or actually strike that. B is going to be the weakest acid. Right? Because the only difference is B has no fluorine atoms. There are no electronegative atoms to pull that negative electron density towards themselves. And so B is going to have the highest energy conjugate base, and therefore that's the weakest acid. What about between A and C? Right? A also has 3 fluorine atoms, but an important point here is they're further away, and distance does matter. Let's actually count how many bonds away they are. Here's 1 bond, 2, 3, 4, 5. And in D, the fluorine's also 1, 2, 3, 4, 5. So A is a stronger acid than D because there are more fluorines, right? 3 instead of 1. But C is a stronger acid than A because the same number of fluorines are closer to the negative charge in the conjugate base. All right, so if we put these in order then, the weakest acid would be B, the next strongest would be D, the next strongest would be A, and the strongest is C. So B, D, A, C. Our answer here is B. The next structural feature that can affect the strength of an acid is bond strength. Bond strength is the dominant effect when the atom losing the hydrogen atom is in the same column of the periodic table. That's important to repeat, right? It has to be the atom losing the hydrogen atom and those atoms have to be in the same column of the periodic table to make this comparison. You'll see why this is important later, because in future problems we'll have to choose electronegativity or bond strength. We can't apply both of these principles at the same time. And this principle relies on valence bond theory. So remember, a covalent bond is when two atoms share electrons, and as they begin to move closer together, as we move from case 1 to 2, right, the energy begins to decrease because of the nucleus electron attractions between the two atoms. Now we're also gaining these electron-electron repulsions and these nucleus-nucleus repulsions, but the nucleus electron attractions outweigh the other forces, and so energy begins to go down until we get to some minimum. Now, to explain how that sharing of electrons happens, we use valence bond theory as one of our theories. And valence bond theory says that that sharing takes place by overlapping the orbitals of each atom together. And you can see that in case 3 here in the bottom right corner. It looks like the electron cloud of one atom has overlapped with the electron cloud of another, and that increases the electron density in the middle, right? That's what you need to form a bond. You've got to have a lot of electron density in between the two nuclei so that you can maximize the nucleus electron attractions and minimize the nucleus-nucleus repulsions. This was our definition of a covalent bond. So again, to summarize, covalent bonds are formed when two atoms' electrons are shared between the two nuclei, and the electrons are shared when the orbitals of those atoms overlap. And here's a third point that I want to make on this slide. The closer in size the orbitals are to each other, the better and the stronger the bond is, the better the overlap will be. And in this picture in the bottom right corner, you can see I'm showing you the degree of overlap in this kind of Venn diagram picture. The better the overlap, the stronger the bond. So here are two hypothetical cases. We don't know what the actual atoms are, but what I'm showing on the left and the right are two different atoms, and the blue areas are showing you the volume or the size of the orbitals that each electron resides in. On the left-hand side, you can see that the orbitals are similar in size. And if we imagine overlapping them with each other, right, we get a Venn diagram picture in the bottom left here that looks like this. And the overlap looks pretty good. There's a large area where the electron density has been increased in between the two nuclei. That's what you need for a good covalent bond. On the left-hand side, though, we have two orbitals of very different sizes. And by different sizes, we also mean different energies. And when these orbitals overlap with each other, you can see that the area of overlap right here is very small compared to the rest of the orbital, the locations where the electrons could be at other times. And so we have not increased the amount of electron density to a great extent in between the two nuclei of these atoms. And so the left case represents similar sized orbitals, better overlap, and a stronger bond. Whereas the right-hand side illustrates dissimilar sized orbitals, poor overlap, and a weaker bond. All right, so how do we put that all together then to predict the strength of an acid? Well, again, this is the dominant effect for atoms losing the hydrogen that are in the same group or column of the periodic table. And the key point here is that as bond strength decreases, acidity increases. So if I look at this series here, right, I'm kind of looking at a space-filling model that also shows me the size of the orbitals, right, that need to overlap to make a covalent bond. So we know that as we move down the periodic table, atomic radius increases because we're getting more shells on top of other shells. So iodine is the biggest of this series. All right, let's just write that down. Iodine has the biggest orbitals. And because of that, those orbitals are going to overlap the poorest with the hydrogen atom. Right, so we've got poor overlap. And poor overlap means a weak bond. And then the connection you want to make on this slide is a weak bond means a strong acid. Right, because remember, in order for an acid to be an acid, it has to donate the proton. We have to dissociate or break that hydrogen conjugate base bond. And so weak bonds are strong acids. All right, if we do that same analysis on the opposite end of this series, right, fluorine is very similar in size to a hydrogen atom, right? It's the smallest in this series. And small means good or better overlap. It's always a comparison. Better overlap means stronger bond, and a stronger bond to hydrogen means a weaker acid. Right? And then we could do the same analysis for those in between. So if we're just looking at the acids of group 7 in the periodic table, it looks like acidity is increasing as we move down the periodic table. HF is the weakest, HI is the strongest. All right, let's apply this principle now to some organic compounds. We have an alcohol, a thiol, and a selenol shown here from top to bottom. Don't worry about the names, we'll talk about functional groups later. But what's important to realize here is that it's the oxygen, the sulfur, and the selenium atom that are going to be losing the hydrogen atom, right, in an acid-base reaction. And so if we find oxygen, sulfur, and selenium in the periodic table, we see that they're all group 6 atoms. They're in the same group. So that means we have to apply the bond strength principle. All right, and they are arranged top to bottom the same way they are in the periodic table. Oxygen is above sulfur, sulfur is above selenium. So that means that as we go down the periodic table, size is increasing. Oxygen, it has the smallest orbitals, and selenium is going to have the biggest orbitals. And what that means is oxygen's orbitals will be the closest in size to hydrogen's. Therefore, we'll get the best overlap, and the best overlap means the strongest bond. The strongest bond should be the weakest acid. And if we look at the pKa values for these compounds, we see that that's true. Right? The pKa of the alcohol is around 16. Okay, remember, the bigger the pKa, the weaker the acid. And the pKa of the selenol at the bottom is 5.2. So that's a huge difference. Each pKa unit difference is a factor of 10. All right, so in summary again, the alcohol here is the weakest acid, and the selenol is the strongest. Now, one point that I want to make, because we're using this word strong, right? These are comparison words, weak est and strong est. We're not necessarily saying weak and strong. All of these acids are weak acids, right? All of these acids, right? Let's make that clear. All of these acids are weak. right? If we were to find the Ka for all of them, it would be 1 times 10 to the negative 15.9, 1 times 10 to the negative 10.6, and 1 times 10 to the negative 5.2. Those are pretty small Ka values, right? They're all less than 1, right? So this is always a comparison, not an absolute. All right, take a break now, hit the pause button, and see if you can answer this question. I've given you 3 compounds, dihydrogen sulfide, water, and ammonia. And don't look these up on Google. See if you can predict which of these 3 acids is the strongest by applying the electronegativity and the bond strength principle. Go ahead and take a break and see if you can get that done. All right, what did you come up with? The periodic table is here so that we can compare the atoms that are losing a hydrogen atom. So let's highlight those. We have sulfur, oxygen, and nitrogen. So here's sulfur, here's oxygen, and here's nitrogen. So it looks like we're going to have to apply both principles because we do have atoms losing hydrogens that are in the same row, nitrogen and oxygen, and we also have atoms that are losing hydrogen in the same column, oxygen and sulfur. So let's start with nitrogen and oxygen and make that comparison. We know that as we move left to right across the periodic table, electronegativity is increasing, right? And that's the principle that we're going to use for atoms that are in the same row. So oxygen is more electronegative than nitrogen, and therefore the conjugate base of water will be more stable, right? The oxygen can pull the electron density closer to itself. The more stable the conjugate base, the stronger the acid. So water is a stronger acid than ammonia using the electronegativity principle. We're not saying strong, we're saying stronger than something else. Okay, now let's compare water and dihydrogen sulfide. Those 2 atoms that are losing hydrogens are in the same column, and we know as we move down a column, size is increasing, the orbital sizes. Bigger orbitals have poorer overlap. Poorer overlap means weaker bond, and weaker bond means stronger acid. So by that analysis, dihydrogen sulfide is a stronger acid, not strong, stronger acid than water. So you can see here we've got a clear order. Dihydrogen sulfide is the strongest, next is water, next is ammonia. So the answer here is A. And to arrive at that conclusion, we used both the electronegativity principle and the bond strength principle. The third and final structural effect that can help us predict relative acidities is resonance. And resonance trumps everything else, right? If you're considering resonance, that's usually the most important factor, the dominant factor above electronegativity and bond strength. And so the resonance argument goes that the more resonance there is in a conjugate base, the better. The more stable the conjugate base is, and the more stable the conjugate base, the stronger the acid. So let's start with an inorganic example. Here we're comparing sulfuric acid to sulfurous acid, H2SO4 and H2SO3. And the rule of thumb for oxyacids is the greater number of oxygen atoms, the more resonance structures can be drawn in the conjugate base, and therefore the stronger the acid. So we see that here in this comparison. If you look at the Ka values on the right, you see that the Ka for sulfuric acid is much larger than the Ka for sulfurous acid. More oxygens means more resonance, means more stable conjugate base, means stronger acid. If we draw the Lewis structures of sulfuric acid and sulfurous acid, we see that this is true. So the conjugate base of sulfuric acid is at the top. Notice that we've lost one hydrogen from one of its oxygens. And I can draw 3 obvious resonance structures to delocalize that negative charge. Right? I can use a lone pair on the oxygen that's negative to form a new double bond to the sulfur atom, but only if I move one of the pairs of electrons in an existing bond out of the way. So in this case, I moved the top bond to the top oxygen, right? Because sulfur can't have more than 6 bonds. And that gives me the resonance structure on the right. Okay, and I can do this again, right? I can form a new double bond with a lone pair on oxygen to sulfur as long as another bond gets out of the way so that I don't have more than 6 bonds. And so one of these double bonds, that pair of electrons can move out to oxygen to give me the resonance structure on the right. So there are 3 obvious resonance structures I can draw here. And you might imagine doing the same on the bottom, right? If you use this pair of electrons to form a double bond to that sulfur, you might then push these electrons out to oxygen, and that gets you back to the very first resonance structure. Okay, so I would say that there are 3 major contributing resonance structures for the conjugate base of sulfuric acid. If we do the same thing for sulfurous acid, we see that there are only 2. And so the principle here is more resonance in the conjugate base means that we can spread the electrons out more or over more atoms. That's called charge delocalization. That makes the conjugate base lower in energy, more stable. And the more stable the conjugate base, the further the equilibrium will lie towards that conjugate base, which means a bigger Ka and a stronger acid. More resonance, stronger acid. Let's look at an example of how resonance applies in organic compounds. So I'm comparing 2 acids here, ethanol on the top and acetic acid on the bottom. You're probably familiar with acetic acid. It's the principal component in vinegar. So both structures are very similar, right? Ethanol has 2 carbon atoms. Acetic acid has 2 carbon atoms. Both have an oxygen-hydrogen bond. That's the bond that's going to dissociate in our acid-base reaction. The only difference is acetic acid also has this carbon-oxygen double bond instead of 2 single bonds to hydrogen. Let's see how that has an effect on the conjugate base. So again, we're imagining a dissociation reaction here. The oxygen-hydrogen bond is breaking towards oxygen, always towards the more electronegative atom. And that's going to give us a proton, H+, and a conjugate base, right? Don't forget, each of these oxygens start off with 2 lone pairs. That has to be true if they're neutral. And so they'll have 3 lone pairs in the conjugate base and be negatively charged. And the difference in these 2 conjugate bases is resonance. Both of them have an oxygen with 3 lone pairs and a negative charge, but only in the conjugate base of acetic acid, which we call acetate. Remember, ATE means an oxygen with a negative charge. In acetate, we can draw 1 resonance structure, right? I'm using curved arrow notation here to show that the negative oxygen can use a lone pair to form a double bond with the adjacent carbon, but only if some bond gets out of the way, because carbon can't have more than 4 bonds. And so a pair of electrons in the double bond moves out to this oxygen. And that gives me the resonance structure on the right. So remember, resonance isn't real. Electrons really aren't moving back and forth in between atoms. But we know that the real conjugate base structure is an average of these 2 resonance structures all the time. And because averages are difficult to draw, we draw the individual Lewis structures and appreciate that the average exists all the time. And so that negative charge is distributed over 2 oxygen atoms. We call that electron delocalization. It's delocalized, it's spread out over 2 oxygen atoms. That is a stabilizing effect. The conjugate base of acetic acid is more stable, much more stable than the conjugate base of ethanol. And the more stable the conjugate base, the bigger the Ka. And that's what we see here, right? A Ka that's much bigger, right? 10 to the negative fifth compared to the Ka of ethanol, 10 to the negative 16. Right? And we could look at pKa values too. The pKa value of ethanol is very large, 16. That's a weak acid. The pKa of acetic acid is small, 4.7. That's a stronger acid. And so resonance has a big impact here, right? If we just say 16 minus 5, that's 11. That means that acetic acid is 10 to the 11th times more acidic than ethanol. So resonance has a huge impact. It trumps everything else, usually. So this is an interesting example. We're going to compare 3 different functional groups. A carboxylic acid, which is defined as a carbon-oxygen double bond with an OH attached. A phenol, which is a benzene ring with an OH attached. And then a simple alcohol, which is any carbon group. Right? That doesn't have to be a 6-membered ring. Could be any carbon group with an OH is called an alcohol. And right away, what we see is that some of the conjugate bases of these acids can do resonance and some cannot. So let's start with the one that can't. The alcohol at the bottom can do no resonance. Right? I can draw a conjugate base. Right? I can dissociate the oxygen-hydrogen bond. Right? And I didn't draw it, but there's also a proton here. Right? And I get a conjugate base, but it's not stabilized by resonance. Right? If you think that you can do this, right, be careful. You can't. Right? There are no bonds that can get out of the way, and carbon can't have more than 4 bonds. Don't forget, there's a hydrogen here. And so if you were to try to attempt to draw that mechanism, you'd end up with a conjugate base, a resonance structure that violates the octet rule. So there's no resonance here, right? No electron delocalization. In the top 2 cases, we do have resonance. We've already seen the resonance that I can draw for acetate, right? 2 resonance structures. And now you can see there are also resonance structures I can draw for the conjugate base of phenol. Okay, so I'll draw a mechanism. Right? The oxygen can use its lone pair to form a double bond to the adjacent carbon, but only if something can get out of the way, because carbon can't have more than 4 bonds. So what gets out of the way is this double bond. It just moves to this adjacent carbon atom as a lone pair. Right? I followed all the rules of resonance. The numbers of electrons haven't changed. The bonding order of the atoms hasn't changed. The total charge hasn't changed, just the arrangement of electrons. And I can continue to draw resonance structures and draw the mechanisms to show how I get from left to right. So I could use this lone pair to form a double bond to the carbon next door, as long as these electrons got out of the way. Right? This is called electron pushing. Do you see how pushing one pair of electrons pushes another pair out of the way? Okay, and I could go all the way around this ring like that. Form a double bond here, and push this pair of electrons out of the way to that carbon. And then finally, push this pair of electrons to the adjacent carbon, form a double bond, and then push a pair of electrons out to oxygen. That gets me to the very first resonance structure. Now, the point that I want to make here is more resonance structures isn't necessarily better. So if we look at the pKa values, we see that the carboxylic acid is the strongest of this series, right? pKa of 4.5. But it only has 2 resonance structures. How can that be? Well, the answer is it's better to delocalize the negative charge over more electronegative atoms than it is to not do that. So the conjugate base of acetate has that negative charge delocalized over 2 oxygen atoms, right, which are highly electronegative. Whereas the conjugate base of phenol has the negative charge delocalized over 1 oxygen atom and 3 carbon atoms. Right? That's not quite as good. Carbon is not very electronegative, and negative charges on carbon then are not very stable. All right, so the summary is it's always better to delocalize negative charge over the most electronegative atoms possible. Now, phenol is definitely a stronger acid than the alcohol on the bottom because it does have resonance. But the 4 resonance structures for phenol's conjugate base are not quite as good as the 2 resonance structures for the carboxylate at the top. A key skill that we'll want to master in this course is determining whether an acid-base reaction lies far to the right or far to the left. So here you can see we have an acid, phenol, reacting with a base, hydrogen carbonate. You might know that as bicarbonate. And we know the pKa values of all the acids in this equilibrium. So the conjugate base of phenol is the phenoxide anion. Remember that IDE means negatively charged. So there's our conjugate base of phenol. And hydrogen carbonate accepts the proton from phenol to become carbonic acid. And so I've given you the pKa values of phenol, of hydrogen carbonate, because it could lose that hydrogen too, and of carbonic acid. And what we want to know is, does this equilibrium lie far to the right or far to the left? In other words, what is the KEQ value for this equilibrium? Not the Ka. What is the KEQ for the entire reaction? And so I don't want to derive the equation on how we figure that out. I just want to give it to you so that we can use it. All right, so one thing to keep in mind is that the equilibrium, this equilibrium, we can tell right away lies to the left. And that's because equilibria always lie towards the weaker side. Right? That seems strange. We don't associate weak with a lot. But weak, remember, really means low energy. And so an equilibrium is always going to lie towards the side with the lowest energy. And we can tell right away that phenol is the weaker conjugate acid, pKa 10, than carbonic acid, pKa 6.4. So even without doing any math, and we'll do the math in the next slide, we can see that this equilibrium should lie towards the left, towards the weaker side. Now let's do the math. All right, so here's the math. If you want to calculate the equilibrium constant for an acid-base reaction, you're going to use this equation right here on the top. It says that the KEQ equals 10 to the power of a negative, and then in brackets, the pKa of the acid on the left minus the pKa of the acid on the right. All right, let's do that math. Right, so the KEQ here would be 10 to the negative, and then who is the acid on the left? It's phenol, right? And phenol has a pKa of 10. So 10 to the negative 10 minus 6.4, which is the pKa of the acid on the right. If I work that out, I get 2.5 times 10 to the negative 4, right? And that tells me that this equilibrium lies to the left. That's a small equilibrium constant. It's less than 1. Lies to the left, right? And I figured that out just from pKa values. Now, an important question here is, what about hydrogen carbonate? I didn't use its pKa value in this equation. And that's because hydrogen carbonate is not acting as an acid. It's the proton acceptor, right, as we move left to right in this equilibrium. So that makes it a base, right? In other words, I've given you too much information here. Since hydrogen carbonate is not acting as an acid, we don't need its pKa, right? We ignore that. All right, so you have to be careful, right? You only use the pKa's for the acid on the left and the acid on the right. We also need to be able to compare the strengths of organic bases. So a classic question in the future might be, who is a stronger base, ammonia or pyridine? And we could come up with a whole list of structural features that help us compare bases, but I've got a simpler solution. The simple solution is don't look at the base, look at that base's conjugate acid. So the conjugate acid of ammonia is the ammonium ion. Remember, conjugate acids have one more hydrogen than the conjugate base. And the conjugate acid of pyridine is the pyridinium ion. And you can look up the pKa's for acids easily in a table, right? And you would see that the pKa for the ammonium ion is 9.3 and pyridinium 5.2. Once we know the relative strength of an acid, we can infer the strength of the base. Use corollary. The stronger the conjugate acid, the weaker the conjugate base. Let me say that again. The stronger the conjugate acid, the weaker the conjugate base. So if I look at the conjugate acids at the bottom, the pyridinium ion, for whatever reason, is the strongest conjugate acid, has the lowest pKa. And that means that pyridine, its conjugate base, is the weakest when comparing these two. We could state the corollary different, right? We could say the weaker the conjugate acid, the stronger the conjugate base, right? And that helps us see that the ammonium ion is a weaker conjugate acid, right? Higher pKa, and therefore ammonia is the stronger conjugate base. Again, be careful. These are relative terms, stronger and weak est. We're not saying strong and weak. Those would be absolute terms. But ammonia is a stronger base than pyridine. And we arrived at that conclusion by looking at the pKa values of the conjugate acid. So if you can make conclusions about conjugate acids, then you can infer those same conclusions for conjugate bases. All right, let's practice some of this. Go ahead and pause the video and see if you can determine what is the KEQ for this acid-base equilibrium. Again, the hint here is make sure you can first pick out who is the acid on the left and who is the acid on the right. All right, what did you come up with? Who is the acid on the left? Well, the only way to figure that out is to look to see who's donating protons and who's accepting protons. It looks like the alcohol is accepting a proton, right? We're starting with an OH group that has one hydrogen, and we're ending with that oxygen having two hydrogens. So that means that that must be the acid. Or sorry, that must be the base. And HCN is donating the proton, and so it must be the acid. All right, so we've picked out who is the acid on each side. That tells us that I don't need the pKa for the alcohol, right, in this equation. Now I can do my math, right? The KEQ is equal to 10 to the negative acid on the left minus acid on the right. And if I do that math, I get 1 times 10 to the negative 12th. So this KEQ, this acid-base reaction, lies far to the left. And what that means is, in practical terms, is HCN is really not a strong enough acid to protonate, to put a hydrogen on the alcohol group in this organic compound. That will have important implications when we start looking at chemical reactions later. In this question, we see 5 conjugate bases of acids. The acids aren't shown, but they're conjugate bases and the atoms that have lost the hydrogen atom are those with lone pairs and are negatively charged. And what this question wants to know is, which of these conjugate bases cannot be stabilized by resonance? In other words, there are no good resonance structures that can be drawn. See if you can figure that out, and we'll come back and work on it together. All right, the next question we might have is, where did I come up with all these pKa values, these numbers? Well, I looked them up in a table like this. Chemists have done experiments to figure out the Kas and then therefore the pKas of common organic acids and inorganic acids. So one skill that will really help us in this course is to memorize the pKa values for a small group of compounds. And so that's what I'd like you to do. I'd like you to memorize the pKa values for these compounds. Now, this is a very small list, but this will be enough to get us started, because what we'll see in future lectures is that we can infer the pKa value of compounds that may not be on this list, but look like compounds that are on this list. So let me give you just one example. Right, let's start with ethanol. Ethanol has a pKa of 16, according to this table. Right, and you can see the structure of ethanol has 2 carbons and an OH group. Well, maybe I haven't memorized the pKa for propanol. Right, and let me write propanol at the top. That's CH3, CH2, CH2, OH. So even though I haven't memorized a value for propanol, when I look at the structure, I see that it's very similar to ethanol. The only difference is 1 carbon atom. And so I could probably infer that the pKa value for propanol, and in fact all alcohols, right, where I have a carbon group attached to an OH, is probably around 16. And that's the real power of this table, right? We'll memorize a small group of pKa's and then use that to infer the approximate, that's what the squiggly line means, the approximate pKa for structures that look similar. All right. Also, the way to interpret this table is I've given you the formula for the acid in the 3rd column here, and also the formula for the conjugate base in the 4th column. Okay, and notice that the conjugate base always has 1 less hydrogen atom than the conjugate acid. Now, what's not shown here are lone pairs. You would have to figure that out. You could put those in if you wanted to. And then in the very last column, I've also given you the conjugate base name, something that we can call it, right? Chloride, acetate, phenoxide. So these names refer to the conjugate base column. All right, so the best way to memorize this maybe is to make some flashcards, right? And we'll add a couple more compounds to the list as we move throughout the course, but this will be good enough to get us started. Another important point I want to make about this table is if you organize the table, right, according to pKa, right? In other words, we have the smallest pKa at the top and the largest pKa at the bottom, right? If we sort it, then we can make some conclusions about conjugate acids and conjugate bases, right? So small pKa means strong acid. So that means that in this series, hydrochloric acid is the strongest and methane is the weakest. And again, using that corollary we used in a previous slide, that can help us to infer the strength of conjugate bases. So remember, the stronger the conjugate acid, the weaker the conjugate base. So chloride is the weakest conjugate base in this series. And I think that makes sense, right? We're all familiar with a compound sodium chloride, right? NaCl-. And chloride doesn't accept hydrogens to become hydrochloric acid, right? If it did, sodium chloride would be pretty toxic. Okay? In the same respect, right, the conjugate base of methane, this carb anion, right, we've got a carbon with a lone pair and a negative charge, okay, is the strongest conjugate base in this series. All right, so again, by memorizing pKa values for acids, you can infer the strengths of their conjugate bases. Another key point in this chart, right, is that if we look at any conjugate base, let's say hydroxide, right, we could conclude that hydroxide is a strong enough base to react with all of the conjugate acids above it in this table, right, to give me KEQ values that were much bigger than 1. Right, so that's really important. Let me say that again. If you're looking at a table where pKa is sorted from smallest to largest, right, the conjugate base is always able to remove hydrogens from all the conjugate acids above it. Right? And you can figure that out just by looking at the table and not doing the math. So here in this slide, I've shown you just a subset of that table, just acetic acid and water, and I've written the acid-base equilibrium when those two react on the top. And a key question that we're going to want to ask ourselves in the future frequently is, can this base remove a hydrogen from this acid? Right? Is hydroxide strong enough to react with acetic acid to give me a KEQ much bigger than 1? And if we look at the table below, even without doing any math, we could conclude yes. Right? Hydroxide, the conjugate base, can react with all of the conjugate acids above it to give me KEQs bigger than 1. Right? So acetic acid will react with hydroxide to give us acetate and water. KEQ would be bigger than 1. If you wanted to do the math, you could, right? Because you have the pKa values here. Acetic acid is the acid on the left. Water is the acid on the right. And so if we use that equation we saw before, right, we get a KEQ of 10 to the 11th. That's very big. This equilibrium lies far to the right. So there's two ways to use the table. Use the numbers to actually calculate KEQ, or just look at the list, the order of the table qualitatively. The conjugate base of any acid can react with all of the conjugate acids above it to give you KEQs bigger than 1. Let's do that one more time. All right, the question might be, can hydroxide react with ethanol to remove its hydrogen, to accept a hydrogen, and give me a KEQ much bigger than 1, right? Does this equilibrium lie far to the right? Okay, let's do it qualitatively first. Here's hydroxide in my subset of the bigger table, right? That's the base. And ethanol, the conjugate acid, is below hydroxide. And so even without doing any math, I can conclude that hydroxide's not a strong enough base to react with ethanol significantly. The KEQ would be less than 1. All right, now let's do it quantitatively. We have the pKa values, so we can do the math. Right? Ethanol, right, has a pKa of 16. That's the acid on the left. Water has a pKa of 15.7. That's the acid on the right. And if I do my math, yep, I get a KEQ that's less than 1. We have a negative exponent here. So a question might be, can sodium hydroxide react significantly with ethanol to give us the conjugate base of ethanol? And the answer would be no, right? It's not a strong enough base. All right, let's end with this question. This is really where we're headed in future lectures. You can see we have a pretty complex organic compound here. There are lots of carbon atoms, and more importantly, there are lots of hydrogen atoms. And if we're writing an acid-base reaction with this compound, we need to know which of these hydrogens is the most acidic. In other words, if a base were to accept a proton from this compound, which one gets accepted first, right? That's the same question. The most acidic proton always gets accepted first. Now, if you look in our previous table, you won't find this compound in it, right? But you can really analyze this as 5 separate problems, right? So if you look at proton A, right, that looks like a hydrogen that's attached to or part of a carboxylic acid. And so go back to that previous table, and next to hydrogen A, write the pKa for a carboxylic acid, right, acetic acid. And then do the same for all the other protons, right? Look at proton B and ask yourself, what is that the most similar to in that previous table? And then write the pKa next to it. Once you've done that for all of these hydrogens, then whichever pKa value is the lowest, that will tell you what the most acidic hydrogen is. And in the future, that will let us know which one gets removed first in an acid-base reaction. So go ahead and give that a try, and then we'll come back and work this out together. All right, this is a tough one. So if you had a hard time figuring this out, don't feel bad. This is going to take a little bit of practice. So I already gave you a clue that the hydrogen in A, right, is part of a functional group called a carboxylic acid. And so if we look at our table, right, acetic acid is the most similar. It has a carboxylic acid. And so that has a pKa of 4.7. Now, this is not acetic acid, so I don't know the exact pKa for proton A, but I can infer that it's probably close to 4.7. All right, B is a little bit tricky. We have a hydrogen atom attached to a carbon. And this looks like a good old-fashioned sp3 hybridized carbon. Did you figure out that this was most like methane, right? CH4. And the pKa for methane is around 60. Now, the hydrogen B is not methane, right? But we can infer that it has a pKa value close to that for methane. All right, for C, that one's even trickier because that one's not in the list. I didn't include arenes in this list. We'll talk about those later, but it has a pKa around 43. Hydrogens directly attached to benzenes. The hydrogen D, the one that's attached to the oxygen, that's a phenol, right? OH groups attached to benzene is the functional group phenol, and that is in the list, and we can infer that it has a pKa around 10. All right, and then finally E, that's a hydrogen on an oxygen with an oxygen attached to a good old-fashioned carbon atom, right? sp3 hybridized. That looks like an alcohol, maybe something like ethanol. So we can infer that E has a pKa around 16. All right, so once we've written the pKa's down, then it's clear to see that it's hydrogen A that's the most acidic here. In other words, if we were to react this compound with a base, A would be the first hydrogen to be removed. An extension of that then, right, D would be the second hydrogen to be removed, etc. This question asks us to determine which of these three equilibria lies furthest to the right. And I've given you a table of some pKa values on the left. So stop and pause and see if you can figure this out. It may be helpful to actually write the pKa values underneath the acids in each equilibrium. Okay, how did you approach this problem? Did you figure out which equilibria doesn't lie to the right at all? In fact, it lies to the left? That's kind of our first step that we should take. So I'm going to put the pKa values underneath of the acids in each case. And again, you have to determine who's acting as the acid on the left and the right. For example, if we just look at A, I know that this compound, acetic acid, is acting as an acid because it's accepting a proton. Right? If I look at the product side, it's donating a proton. If I look at the product side, it's lost its hydrogen. That's our definition of acid, proton donor. And I know that this is the base because it's accepting a hydrogen atom. When I look at the products, it's got one more hydrogen than it had. All right, so first you have to decide who's the acid on each side, and then write the pKa values underneath. Another thing to remember is that an equilibrium always lies toward the weakest side. Right? So I could conclude then that that equilibrium is bigger than 1. It lies to the right because the ammonium ion has a pKa of 10.7, and that means it's a weaker acid than acetic acid. Right? So the weakest side is on the right, the equilibrium lies to the right. Same for B. Right? Potassium hydrogen carbonate, pKa of 10.3. Phenol, the acid on the left, 10. Right? Bigger pKa, weaker acid. The equilibrium lies towards the weakest side. So again, that equilibrium lies to the right. But in C, right, the equilibrium lies to the left. Right? The weakest acid is actually the alcohol, methanol, here on the left. All right, so it's between A and B. And then we could do the math. We could calculate the KEQ for each one of those, right, and figure out which is bigger. Or we could just look at the difference in the pKa values. Right? Without doing any math, I can clearly see that the difference between 4.7 and 10.7 is much bigger than the difference between 10 and 10.3. And so therefore I can conclude that A lies furthest to the right. Right? And if you don't believe or trust or understand that analysis, go ahead and just calculate the KEQ. That's always a guaranteed way to compare reactions to each other.